Earth is 4.5 billion years old. You have been here for 300,000. Something else was here first. Many somethings. Life that turned the sky from poison gas to breathable air. A nuclear reactor that ran itself for hundreds of thousands of years before humans existed. An asteroid that rewrote which species got to survive. And a question two scientists published that shook geology to its core. If something intelligent lived here before us, would we even know? If you enjoy what we uncover, subscribe and stay with us. Let's begin. Close your eyes and picture Earth. Green continents, blue oceans, white clouds drifting over mountain ranges. Now erase all of it. 4.5 billion years ago, this planet was a ball of liquid rock. No crust, no water, no air worth breathing. The surface glowed orange from the heat of constant meteor impacts. Every few thousand years, something the size of a small country would slam into the surface and melt everything all over again. Scientists call this the Hadean Eon, named after Hades, the ancient Greek word for the underworld. That name fits. For 400 million years, Earth was too violent, too hot, and too unstable to hold on to anything delicate. Water that landed here immediately vaporized. Gas that tried to collect around the planet got blasted away by the young sun's radiation. If you had been standing on this planet during the Hadean, the ground beneath your feet would have glowed. The sky above you would have been orange with heat. The temperature at the surface exceeded the melting point of most rock. And yet, something survived. Deep in the crust of Western Australia, inside a place called the Jack Hills, scientists found a crystal. A zircon crystal. Microscopic. You could fit dozens of them on the tip of a pencil, and inside that crystal, locked in atomic structure for 4.4 billion years, was a record of the conditions on this planet that should have been erased 100 times over. Zircon is one of the hardest, most chemically resistant minerals on Earth. Think of it as geology's equivalent of a titanium vault. While everything around it melted, exploded, or washed away, the zircon just sat there, holding its data. Scientists measure the ratios of specific atoms inside it, uranium and lead, and those ratios work like a clock. The older the crystal, the more lead has accumulated from uranium's slow radioactive decay. The Jack Hills zircon clocked in at 4.4 billion years old. That makes it the oldest known piece of Earth that still exists. Older than the continents, older than the oceans, almost as old as the planet itself. But here's where it gets stranger. The oxygen atoms locked inside that crystal carry a specific chemical signature. Scientists read oxygen in two forms, a lighter version and a heavier version. The ratio between them changes depending on whether liquid water was involved in forming the crystal. The Jack Hills zircon's ratio says water was there. Liquid water. On the surface of a planet that most scientists assumed was far too hot and violent to hold any. This is confirmed. The signal is real. What it means is that Earth cooled down faster than anyone expected, formed a crust earlier than the models predicted, and may have had oceans forming and evaporating and forming again, even during the worst of the Hadean bombardment. That changes everything about when life could have started. If water existed 4.4 billion years ago, the window for life to begin opens much wider. And if the window opens wider, then whatever came before us had even more time than we thought. The Jack Hills zircon fits in the palm of your hand. And it just told us that Earth's early history was far less simple than science assumed. The next question is what else that crystal was hiding. The Jack Hills zircon confirmed liquid water existed earlier than anyone expected. But one crystal is a clue, not a conclusion. So scientists kept digging, kept dating, kept reading the atomic signatures locked inside hundreds of zircon grains from the same region. And one of them told a story that stopped the room. A 4.1 billion year old zircon from Jack Hills contained something unexpected trapped inside its structure. tiny flecks of graphite. Graphite is just carbon atoms arranged in flat layers. You find it in pencils, you find it in ancient rock. By itself, it means nothing unusual. Carbon is everywhere in geology, but this graphite had a specific ratio between two forms of carbon, the lighter version and the heavier version, that scientists recognized immediately. Life prefers the lighter form. When living organisms process carbon, build their cells, metabolize energy, they selectively pull the lighter carbon isotope out of their environment. This creates a chemical fingerprint. Ancient biological material from every era of confirmed life on Earth carries that fingerprint. And the graphite inside this 4.1 billion year old zircon carried it too. This is labeled a theory, not confirmed. Scientists are careful about this one, and they should be. These crystals have been buried, heated, pressured, and transformed for 4 billion years. Extreme geological processes can also produce light carbon signatures without any biology involved. The rock's history makes it nearly impossible to rule out a non-biological explanation with complete certainty. But the signal is there, and it has not gone away under scrutiny. If the signal is biological, it means life on Earth began within 400 million years of the planet forming. 400 million years sounds like a long time. On a human scale, it is incomprehensible. On a geological scale, it is fast. Shockingly fast. Some scientists use the word immediately when they describe it in context. Think of it this way. If Earth's entire history were one calendar year, starting January 1st, confirmed life shows up in February. This carbon signal would push the first signs of biology back into the first week of January. That speed carries a heavy implication. If life started almost as soon as the conditions allowed it, life might not be the rare, fragile accident we once assumed. It might be something the chemistry of rocky, wet planets does almost automatically. And if that is true here, it raises urgent questions about every other rocky, wet planet orbiting every other star in the galaxy. But before we can accept that implication, we need something more solid than a carbon ratio in a crystal. We need actual fossils. We need structures we can see, shapes that biology builds and geology cannot fake. And those exist too. They are older than most people realize, found in some of the most remote places on Earth, and they started a debate about what counts as life that is never fully closed. The oldest confirmed fossils on Earth were sitting in a belt of ancient rock in Canada, waiting for someone to look in the right place. Before we get to the fossils in Canada, we need to stay with the carbon signal one moment longer. Because this debate, the one over whether the Jack Hills graphite is biological, reveals something important about how science actually works when the stakes are this high. The team that published the carbon finding did everything right. They measured the carbon isotope ratios carefully. They compared their results to confirmed biological signatures from every era of life they could access. The signal matched. They published. Other scientists pushed back. The graphite could have formed from abiotic chemistry, meaning chemistry with no life involved. The crystals had been metamorphosed, heated under pressure for billions of years, and metamorphism can alter isotope ratios in unpredictable ways. Here is what makes this hard. To prove the carbon is biological, you need to rule out every geological process that could produce the same signature. In fresh rock from a recent geological formation, you can do that. In a 4 billion year old zircon that has been through every form of geological stress imaginable, the task becomes close to impossible. The rock has been through too much. The signal survives. The certainty does not. So science sits with this. A carbon ratio that looks biological in a crystal that is old enough to matter enormously, with a geological history that prevents any clean verdict. The researchers who found it are careful. They say potentially biogenic. They do not claim confirmation. And that carefulness is exactly why this finding remains alive in the scientific literature. A reckless claim would have been dismissed. A careful one stays on the table. What this chapter is really about, though, is the problem of detection. How do you find evidence of something that existed 4 billion years ago on a planet that has been actively destroying its own surface the entire time? Plate tectonics recycles the ocean floor every few 100 million years. Erosion grinds rock to dust. Heat and pressure transform everything. The geological record from Earth's earliest eons is vanishingly thin. Most of it is gone. The Jack Hill's zircon survived because zircon is nearly indestructible. They are geological outliers. The fact that they exist at all, and that they contain readable information, is close to miraculous from a statistical standpoint. Everything else from the era is simply absent. This creates a problem that extends far beyond carbon ratios in ancient crystals. If you are trying to detect something that existed before recorded history, before fossils, before complex chemistry left durable traces, you are working with almost nothing. You are reading smoke signals from a fire that burned 4 billion years ago and was buried under a mountain. Scientists accept this limitation and work within it. They use every indirect signal available: isotope ratios, crystal structures, mineral chemistry, trace elements. They build cases out of convergent evidence rather than single proofs. And every now and then, that approach produces something extraordinary. In Quebec, Canada, deep inside some of the oldest exposed rock on Earth, a team found structures that stopped being ambiguous. The Nouveau-Aghituc Belt in Quebec, Canada, holds some of the oldest exposed rock on the surface of the planet. The rock itself has been dated to somewhere between 3.77 billion and 4.28 billion years old, depending on which isotopic system you trust. Inside that rock, embedded in ancient seafloor sediment that formed around hydrothermal vents, scientists found something they recognized: tubes. Tiny filamentous tubes made of hematite, which is a form of iron oxide, some straight, some twisted, some branching. The tubes range in size from thinner than a human hair to just barely visible to the naked eye, and their shapes match almost exactly the structures left today by iron metabolizing bacteria that live around modern hydrothermal vents on the ocean floor. This is confirmed at minimum 3.77 billion years old. The upper estimate of 4.28 billion years is still debated, but the lower bound is solid. Here is why hydrothermal vents matter. For decades, the leading theory about where life began involved warm, sunlit, shallow ponds on the early Earth's surface. Ultraviolet radiation from the young sun would have driven chemistry. Organic molecules would have accumulated. Eventually, something self-replicating would have emerged. That model still has supporters. But hydrothermal vents offer a different picture. They pour superheated water rich in minerals and chemical energy directly into the cold, deep ocean. They create steep chemical gradients, places where two very different chemistries meet, and those gradients can drive reactions that build complex molecules without any sunlight at all. Life near modern vents survives entirely without photosynthesis. It is chemically powered from below, not light-powered from above. If the Nouveau-Aghituc structures are biological, and the chemistry surrounding them, including the presence of carbonates and carbonaceous minerals pointing to oxidation and organic activity, supports that conclusion, then life on Earth began deep underwater, in the dark, powered by the heat of the planet itself. Pause on that for a second. The first life on Earth may have never seen sunlight, ever. Some scientists remain cautious about the Nouveau-Aghituc fossils. The argument is familiar by now. Ancient rocks have complex histories, and some inorganic processes can produce tube-like mineral structures. But the chemical context here is stronger than in the Jack Hill's zircon case. The combination of tube morphology, carbon chemistry, and associated minerals creates a convergent case that most researchers find persuasive. For the rest of this story, we will treat the Nouveau-Aghituc microfossils as confirmed life. Because at 3.77 billion years old, even the minimum date is extraordinary enough. Life existed on this planet within less than a billion years of its formation. It lived in the dark, it ate minerals, and it left behind structures that survived 4 billion years of geological punishment. Everything that came after, all the oxygen, all the complex animals, all the extinctions, all the civilizations, built on that foundation. But to understand how this microscopic, invisible life eventually transformed the entire planet, you need to understand what happened next. And what happened next started quietly, then became the most violent chemical event in Earth's history. For the first 2 billion years of life on Earth, nothing you could see with the naked eye existed. No plants, no animals, no fungi, just microbes. Single-celled organisms living in oceans that look nothing like today's. The water was warm in places, cold in others, and full of dissolved iron that gave it a greenish tint. The sky above was a pale orange haze, rich in carbon dioxide and methane, with almost no oxygen at all. Into this world came cyanobacteria. These are among the earliest photosynthetic organisms ever confirmed in the fossil record. They showed up in the rock record by 3.5 billion years ago, confirmed in the Dresser Formation in Western Australia, which we will return to in a later chapter. They were small, simple, and from the outside, completely unremarkable. But they were doing something that nothing before them had done at anything close to this scale. They were splitting water molecules using sunlight, pulling out the hydrogen for energy, and releasing the oxygen as waste. Oxygen, expelled as garbage. For hundreds of millions of years, this waste product went nowhere dangerous. The early oceans were loaded with dissolved iron. Every molecule of oxygen that cyanobacteria released reacted almost immediately with that iron, binding together to form iron oxide, which settled to the seafloor as rust-colored sediment. These layers built up over time into what geologists call banded iron formations. Some of the biggest iron ore deposits on Earth, the ones we mine for steel today, were made by cyanobacteria dumping their oxygen waste into ancient seawater, billions of years before humans existed. The oceans were acting as a giant sponge. Every time cyanobacteria released oxygen, the iron absorbed it. The oxygen never reached the atmosphere. The planet stayed anoxic, meaning oxygen-free, decade after decade, million year after million year. But the iron was running out. Slowly the concentration of dissolved iron in the oceans dropped. The sponge was getting full, and cyanobacteria kept photosynthesizing, kept releasing oxygen, kept pushing it into water that was increasingly unable to absorb it. The moment the oceans became saturated is one of the most important thresholds in the history of this planet. Once the iron was gone, the oxygen had nowhere to go except up. And when it finally reached the atmosphere in quantities large enough to accumulate, everything changed. The bacteria doing this had no plan, no awareness, no intention. They were just eating sunlight and expelling waste, the same way they always had. They had been doing it for so long that by the time the consequences arrived, they had already been quietly building toward this for hundreds of millions of years. What happened when the oxygen finally crossed the threshold wasn't a slow transformation. From a geological perspective, and this happened fast. And for most of the life that had evolved to survive in an oxygen-free world, it was catastrophic. The chemistry of those pre-oxygen rivers, full of iron and sulfide and metals that can't survive in today's air, is the next piece of this story. Because it shows just how different Earth was, and how completely life rewrote it. Picture a river. Probably you picture something clear, or maybe brown from sediment after rain. You picture water that smells like mud, moves fast around rocks, and supports fish and insects and plants along the banks. Erase that image completely. Before the Great Oxygenation event, Earth's rivers were chemically unrecognizable. They ran loaded with dissolved iron and sulfides. In high enough concentrations, dissolved iron gives water a dark reddish or greenish tint. The water would have smelled of sulfur in many places, a sharp chemical smell that today we associate with volcanic vents or rotting eggs. Along the banks, there were no plants, no insects, no animals of any kind, just rock, sediment, and the chemical products of a world where oxygen hadn't yet taken hold. The rivers carried minerals that simply cannot exist in today's atmosphere. Detrital pyrite, iron sulfide, and a uranium mineral called uraninite both appear freely in riverbeds from the Archean Eon, the period before the Great Oxygenation Event. Both of these minerals react with oxygen and break down. Pyrite in oxygen-rich water produces sulfuric acid. Uraninite oxidizes and dissolves. You find them in ancient pre-oxygenation river sediments because the air contained essentially no free oxygen to destroy them. After the Great Oxygenation Event, they essentially vanish from the river rock record. Their disappearance is one of the clearest chemical markers scientists used to date when Earth's atmosphere changed. It is a before and after line written in mineralogy. The sulfur isotopes tell the same story from a different angle. Before the oxygenation event, sulfur in the atmosphere behaved in a specific way when hit by ultraviolet radiation from the sun. Without an ozone layer to block those rays, ultraviolet light split sulfur molecules and created an isotope pattern called mass-independent fractionation. This pattern is chemically distinctive. Scientists can measure it in ancient sulfur-bearing rocks and instantly know those rocks formed in an oxygen-free world. After the Great Oxygenation Event, mass-independent sulfur fractionation disappears from the record. Oxygen accumulated. Ozone formed from it. The ozone blocked the ultraviolet rays. The sulfur chemistry shifted, and the change is recorded permanently in the chemistry of rocks from every continent on Earth. Red beds also appear for the first time in the continental record after the Great Oxygenation Event. These are ancient soils stained red by iron oxide, the same rust color you see on iron left out in rain. They form when iron in soil reacts with atmospheric oxygen. Before the oxygenation event, there was no atmospheric oxygen to create them. After, they spread across the continents like a slow tide of rust. Multiple independent lines of evidence, minerals, isotopes, soil colors, all converge on the same moment. All tell the same story. And all of them confirm that before cyanobacteria built up enough oxygen to cross the atmospheric threshold, Earth was a planet with a completely different chemistry. The transformation that came next was not gentle. For the organisms that had evolved over billions of years to live in that oxygen-free world, the new atmosphere was lethal. 2.45 billion years ago, oxygen crossed the atmospheric threshold. And for the organisms that dominated Earth's oceans at that moment, it was a mass extinction that dwarfs anything that came later. The living world at that time was entirely anaerobic. That means every single organism on Earth had evolved to survive without oxygen. Their metabolism, their chemistry, their entire biological machinery was built for a world where oxygen was absent. For these organisms, free oxygen in the environment was not a resource. It was poison. Oxygen reacts. It reacts with almost everything. It attacks the chemical bonds that hold organic molecules together. It generates compounds called reactive oxygen species that rip through cell membranes, damage proteins, and destroy the molecular machinery of life. Modern organisms have built elaborate defense systems against this oxygen toxicity. Antioxidant enzymes, repair mechanisms, protective pigments. But those defenses take millions of years of evolution to build. The organisms living through the Great Oxygenation Event had none of them. As oxygen accumulated in the atmosphere and began dissolving into the upper layers of the ocean, anaerobic organisms died in enormous numbers. They retreated to oxygen-free pockets, deep sediments, hydrothermal environments, the intestines of larger organisms that eventually evolved. Some of their descendants still live in those refuges today, but as a dominant force in Earth's biosphere, the anaerobes lost their world in this event. Scientists call this the oxygen catastrophe, or sometimes the Great Oxidation Event. The word catastrophe is accurate, but here is the paradox at the center of this story. That catastrophe was also the most important prerequisite for everything that followed. Complex eukaryotic cells, the kind with a nucleus and internal structures, require oxygen-based metabolism to generate enough energy to support their complexity. Multicellular animals require even more. The human body burns oxygen in every cell, constantly, and could not function for more than minutes without it. Every living thing with more than one cell. Every plant, every insect, every fish, every mammal, every human being, all of it depends on an oxygen-rich atmosphere. All of it traces back, in a direct chemical line, to cyanobacteria treating oxygen as waste. The catastrophe and the gift were the same event. The timing of exactly why the oxygenation crossed the threshold when it did remains an active area of research. The mechanism, cyanobacteria producing oxygen until the oceanic iron sponge was exhausted, is confirmed. But the precise ecological and geophysical feedbacks that determine the timing are still being worked out. The when is confirmed. The full why is still being modeled. What happened to life after the Great Oxygenation event is a story of slow rebuilding. New organisms evolved that could not only tolerate oxygen, but exploit it. Eukaryotes emerged. Eventually, multicellular life appeared. But before the story reaches complex animals, there is one extraordinary detour that almost no one knows about. Something in a uranium deposit in West Africa built itself. Without any intelligence, without any design, and it ran for hundreds of thousands of years. Before we reach that uranium deposit, we need to stop at the oldest visible life structures on the planet, because they are still alive, and you can walk up and touch them. In Shark Bay, Western Australia, in water so salty that almost nothing else survives, layered dome-shaped structures rise from the seafloor in shallow, coastal water. Some are the size of a fist, some are bigger than a watermelon. They look like rounded grey rocks sitting in rows at the edge of the tide. They do not move. They do not make any sound. They look completely inert. They are alive. These are stromatolites, living colonies of cyanobacteria that build their structures layer by layer, trapping sediment and producing thin mats of mineral material as they grow. A single stromatolite grows only about a millimeter per year. The structures in Shark Bay are the same basic design, built by the same basic organism, using the same basic process that built the confirmed 3.48 billion-year-old fossils in the Dresser Formation of the Pilbara Craton, also in Western Australia. The fossil stromatolites of the Dresser Formation are the oldest unambiguous evidence of complex microbial life on Earth. Unambiguous means scientists look at these structures and agree, biology did this. The shapes, the layering patterns, the chemistry of the surrounding rock all match what biology produces. The debate that surrounds the Nuvuagituk microfossils or the Jack Hill's carbon signal doesn't apply here. Dresser stromatolites are 3.48 billion years old, and confirmed. Living stromatolites still form today only in environments where conditions prevent most grazing organisms from eating them. Shark Bay's extreme salinity keeps away the snails and worms and small crustaceans that would otherwise consume the cyanobacterial mats before they could build up into structures. In normal marine environments, they get eaten. In Shark Bay, they survive. And they look exactly like their ancient counterparts. In 2025, a research team applied an artificial intelligence system to analyze the chemistry of rocks from the Pilbara region. The machine used a technique called pyrolysis gas chromatography mass spectrometry, which breaks rock samples apart and identifies the chemical compounds released. The algorithm was trained on biological and non-biological samples, and then asked to classify ancient rock samples without being told what they were. It identified biogenic molecular patterns in rocks from 3.51 billion years ago, and photosynthetic activity in rocks from 2.52 billion years ago. The system distinguished biological from non-biological material with over 90% accuracy. Machines reading ancient chemistry, confirming life existed before anything with eyes or limbs ever appeared on this planet. Stromatolites are not impressive to look at. They sit in shallow water and grow 1 millimeter per year, and have been doing exactly that for 3.5 billion years. They were photosynthesizing before the ozone layer existed. They built the oxygen in the air your lungs are using right now, and somewhere in the rock record, the chemical traces of that process are still readable. But the next discovery takes the concept of nature running processes without any intelligence to an entirely different level. Because in West Africa, geology did something that humans didn't figure out how to do until 1942. In May 1972, a chemist working at a uranium processing facility in France noticed a number that didn't add up. Uranium from a mine called Oklo, located in Gabon, West Africa, contained slightly less of a specific uranium variety called uranium-235 than it should have. Natural uranium from anywhere on Earth always contains the same percentage of uranium-235, 0.7202%. Always. The laws of nuclear physics set that ratio. It doesn't vary, except this sample was low. Slightly, almost imperceptibly low, but low. The chemist flagged it. A team investigated. They pulled more samples from the mine. Some were even lower. Eventually they found ore containing as little as 0.44% uranium-235, and the calculation revealed that roughly 500 kilograms of uranium-235 were simply missing from the deposit. That is enough fissile material to build several nuclear weapons. The investigation that followed produced one of the most extraordinary conclusions in the history of geology. The uranium-235 was gone because it had already been consumed in a fission chain reaction. Nature had built a working nuclear reactor on its own 1.7 billion years ago. Here is how. Nuclear fission requires two things: enough fissile material concentrated in one place, and something to slow down the neutrons so the chain reaction sustains itself. At Oklo, the uranium ore was unusually rich and concentrated. 1.7 billion years ago, uranium-235 was more abundant in natural ore than it is today, because uranium-235 decays faster than the more common uranium-238, and has been decreasing ever since. Back then, the concentration was close to 3%, similar to the enriched uranium used in some modern power plants. The second ingredient was water. Groundwater percolating through the ore deposit acted as a neutron moderator, slowing the neutrons enough to sustain the chain reaction. The reactor cycled on and off over hundreds of thousands of years, probably in pulses of roughly 30 minutes of active fission, followed by longer cooling periods as the water boiled away and then refilled. Scientists found 16 separate reactor zones inside the Oklo deposit. Each one shows the same pattern. Uranium isotope ratios depleted exactly as they should be if fission occurred. Fission product isotopes including xenon and neodymium, present in precisely the ratios a reactor would produce, and reaction geometry consistent with a self-sustaining chain reaction. Enrico Fermi's team built the first human-made nuclear reactor under a stadium in Chicago in 1942. Nature did it first, by 1.7 billion years. The Oklo reactor is the only confirmed case of a natural nuclear fission reactor on Earth. It operated quietly, regulated itself, and eventually exhausted its fuel. Nobody was there to watch it. Nobody designed it. The geology just happened to arrange the right materials in the right configuration at a moment in history when the uranium-235 concentration was high enough to make it work. But what happened to the nuclear waste? That answer is even more extraordinary than the reactor itself. One of the biggest unsolved challenges in modern nuclear power is what to do with the waste. Spent fuel rods remain dangerously radioactive for tens of thousands of years. Governments argue about storage sites. Engineers design elaborate containment systems to keep radioactive material from leaking into groundwater. The problem is enormous, expensive, and politically contested worldwide. The Oklo reactor in Gabon solved this problem without any engineers. After the reactor shut down, Its fission products, the radioactive byproducts created during the chain reaction, stayed almost exactly where they formed. Scientists examining the Oklo site found that even highly mobile radioactive elements, the ones that tend to travel through rock and water, had migrated only a few feet from their original positions after 1.7 billion years. 1.7 billion years. A few feet. By comparison, modern nuclear waste containment is designed to hold material for 10,000 years. The natural geological chemistry at Oklo contained far more radioactive material in a reactive environment with flowing groundwater for a duration 170,000 times longer. The radioactive byproducts were trapped by the mineralogy of the surrounding rock. Certain clay minerals in the deposit absorbed the fission products and held them in place as the atoms slowly decayed into stable elements over geological time. This discovery is now used by nuclear engineers and geologists when they model long-term waste storage. Oklo is the best natural experiment ever conducted on how rock and groundwater interact with radioactive material over deep time. The data from a 1.7 billion-year-old natural reactor is directly applicable to designing waste storage that needs to last tens of thousands of years. Nature ran an accidental nuclear containment experiment for 1.5 billion years and got a better result than anything humans have yet managed. The radioactive fingerprints left by Oklo are still measurable today. Specific isotope ratios in the ore, particularly xenon and neodymium, produced only by fission, match exactly what the chain reaction would have produced. These signatures are so distinctive that they cannot be explained by any other geological process. They are the nuclear equivalent of a chemical footprint, preserved in stone for over 1 billion years. Two things stand out about Oklo when you step back from the details. First, it confirms that nature can produce conditions usually associated with advanced technology, given the right chemistry and enough time. Second, and more quietly unsettling, it raises a question that becomes more important as this story continues. If a natural process running without any intelligence can produce something as technically specific as a nuclear chain reaction, and leave behind a chemical fingerprint so distinctive that engineers study it today, what would a civilizational process leave behind? What chemical fingerprints would a species burning through fossil fuels and transforming the planet's chemistry stamp into the rock record? That question comes back later in the story, in a form that is much harder to answer than it looks. But first, the story of life on Earth takes a turn into territory that should feel familiar, but is actually completely alien. The next chapter begins about 650 million years ago, with animals so strange they challenge every assumption about what an animal is supposed to be. 635 million years ago, the planet had just come through one of the most extreme glaciations in its history. Geologists call it Snowball Earth, a period when ice may have covered the planet from poles to equator. What survived beneath the ice and in pockets of liquid ocean near volcanic vents began diversifying when the ice retreated. What emerged was life that evolution had never tried before and would never produce again. The Ediacaran period runs from 635 million to 539 million years ago. The organisms that populated this period were soft-bodied, leaving no shells, no bones, and no teeth in the fossil record. What they left instead were impressions in ancient seafloor sediment, flat molds of creatures that lived, died, and sank into fine-grained mud that later turned to stone. Some Ediacaran organisms looked like fronds, others looked like discs. Some resembled air mattresses, flat, ribbed, quilted structures lying on the seafloor. One category, called the rangemorphs, branched like coral but had no mouth and no apparent digestive system. They may have absorbed nutrients directly from the water through their outer surfaces, a feeding strategy with no direct equivalent in any modern animal. Dickinsonia is one of the most studied Ediacaran organisms. It could grow to nearly 4.5 feet long, which makes it the largest organism of its era. It was flat, oval, ribbed, and almost certainly had no internal organs as we understand them. Scientists found fat molecules, specifically cholesterol-like compounds, preserved in the rock around a Dickinsonia fossil in Russia, confirming it was an animal and placing it among the oldest confirmed animal fossils on Earth. But what it ate, how it moved, and whether it had any kind of nervous system remains genuinely unknown. Hautia, confirmed at 560 million years ago, holds the record for the oldest known animal muscle tissue. It was a cnidarian, meaning it belonged to the same broad group as modern jellyfish and sea anemones. Its fossilized fibers match the structure of muscle in cross-section. This is confirmed by multiple research teams. What killed the Ediacaran biota is an open question. Most Ediacaran body forms disappear from the fossil record as the Cambrian begins. A few lineages may have survived and become ancestors of Cambrian animals. Others seem to vanish completely. Whether predation by early Cambrian animals outcompeted them, whether environmental shifts ended them, or whether their preservation in the fossil record simply fails during this transition, is unknown and actively debated. An entire kingdom of life forms, some as large as a person, with no mouths and possibly no movement, lived on this planet for nearly 100 million years. And then they were gone. But gone from the surface does not mean gone from the story. Because research published in April 2026 revealed that the Cambrian explosion, the event that supposedly replaced the Ediacaran world, had been building from within it for much longer than anyone realized. In April 2026, a research team published findings in the journal Science describing fossils recovered from southwestern China that fundamentally changed the timeline of animal evolution. The fossils predated the Cambrian explosion, and what they showed was already complex. The Cambrian explosion, beginning approximately 539 million years ago, has been described for decades as the moment when most major animal body plans appeared in the fossil record seemingly at once. Geologically speaking, it was fast. Over a few tens of millions of years, animals with shells, with eyes, with limbs, with nervous systems, all show up in the rock record in a burst that looks sudden compared to the billions of years that preceded it. The China fossils push that starting line back. Among the organisms preserved in these rocks were the earliest known bilaterally symmetrical animals. Bilateral symmetry means having a left side and a right side that mirror each other, a design that underlies the body plan of almost every complex animal alive today, including humans. Finding it before the Cambrian means this fundamental architectural decision was made in the Ediacaran, not the Cambrian. Other fossils in the same deposit included stalked creatures with what appeared to be tentacles at the top, resembling an inverted wine glass made of tissue. Others were elongated, sausage-shaped organisms with feathery appendages running along their sides. These forms showed active feeding structures, body segmentation, and specialized appendages. None of this was supposed to exist before the Cambrian. The evolutionary toolbox that produced the Cambrian explosion was already open and being used. This matters because it reframes the question scientists were asking. The question was never why did complex life suddenly explode into existence in the Cambrian. The question should have been why did the preservation conditions change in the Cambrian, making organisms with hard shells suddenly visible to the fossil record? The animals were already there. Evolution had already done most of the work. The fossils just weren't being saved. Soft-bodied organisms leave impressions only under specific conditions. Fine sediment, rapid burial, no oxygen in the bottom water to allow decay. Most Ediacaran organisms left impressions in exactly these conditions. As the Cambrian began, many animals started producing shells and external skeletons. Hard parts preserve far more easily and across far more environments. The fossil record fills up quickly, so the Cambrian explosion may have been less an event and more a revelation. The moment the record started capturing what evolution had already built. This single reframing changes how scientists think about the pace of biological innovation. And it raises a question that connects directly to the Silurian hypothesis we haven't reached yet. If complex animals existed before the conditions that would preserve them as fossils, what else might have existed and left no clear trace in later eras of Earth's history? The Cambrian explosion itself deserves a closer look before that question gets answered. 539 million years ago, something happened in the fossil record that confused scientists for over a century. Within a relatively short geological window, most major animal body plans appeared in the rock record for the first time. Eyes, legs, shells, claws, internal skeletons, external armor, complex guts. The diversity that appeared in this window is staggering. Animals that look like distant relatives of crabs, fish, worms, insects, and mollusks all show up within tens of millions of years of each other, after billions of years in which the fossil record shows nothing like them. Charles Darwin himself was troubled by this. If evolution worked gradually, this sudden burst of complexity looked almost like a discontinuity. He considered it a serious challenge to his theory and hoped future discoveries would fill in the gap. They did, just slowly. The Cambrian explosion looks sudden only when you compare it to the nearly 4 billion years of microbial life that preceded it. Zoom in, and the explosion took tens of millions of years. Zoom in further with molecular clock analysis, which uses the rate of genetic mutation to estimate when lineages diverged, and many of the major animal groups split off from each other well before the Cambrian even began. The genetic work had already happened. The body plans were already in development. The Ediacaran fossils we covered earlier confirm this. Bilateral symmetry, muscle tissue, organized body architecture, all of it predates the Cambrian. And the China fossils published in 2026 push even more of the animal story back before the explosion's starting line. What the Cambrian actually brought was shells. When organisms started producing hard calcium carbonate shells and external skeletons, two things happened simultaneously. First, predation escalated. Hard shells developed as protection against animals with hard mouth parts that could now bite and crush. Second, preservation skyrocketed. Hard parts fossilize far more easily than soft tissue. A shell buried in sediment can last 500 million years. A soft body buried in the wrong sediment decays in weeks. The sudden appearance of complexity in the Cambrian fossil record is real, but it reflects a revolution in preservation as much as a revolution in biology. There is one more dimension to this. The Cambrian explosion produced body plans that have persisted with modifications for 500 million years. The basic architectural decisions made in that window, how to build an eye, how to organize a nervous system, how to use a hinged jaw, proved so successful that evolution has worked within those frameworks ever since, rather than starting over. 500 million years of refinement. And underneath all of it, the soft-bodied, mouthless, possibly immobile Ediacaran organisms that came first. The story of life before us is already extraordinary, and it is about to get darker. Because the history of complex life on Earth is also a history of catastrophic interruption. 5 mass extinctions. 5 moments when the planet came close to resetting entirely. And the worst one almost ended the story before it really began. 252 million years ago, something went catastrophically wrong. The Permian-Triassic mass extinction is the largest extinction event in the history of complex animal life. By the time it was over, roughly 96% of all marine species were gone. On land, roughly 70% of vertebrate species died. The event was so severe that scientists sometimes call it the Great Dying. It is the closest complex life has ever come to being completely erased from this planet. The precise cause is still debated, but the leading suspect is massive volcanic activity in what is now Siberia. A geological feature called the Siberian Traps formed over roughly 1 million years as enormous volumes of magma pushed through the crust and erupted across an area larger than the continental United States. The eruptions released vast quantities of carbon dioxide, sulfur dioxide, and other gases into the atmosphere. Global temperatures rose sharply. Ocean chemistry was disrupted. The water became more acidic. Oxygen levels in the deep ocean dropped so severely that vast regions of seafloor became effectively dead zones. Warming alone did not kill everything. The combination of heat, ocean acidification, and oxygen loss worked together across different environments, hitting marine life through multiple mechanisms simultaneously. The recovery from the Permian-Triassic extinction took roughly 10 million years. Some groups never recovered at all. The trilobites, which had survived for over 270 million years through multiple earlier extinctions, went extinct in this event. Groups that were devastated included corals, which effectively disappeared from the fossil record and took millions of years to re-establish reef ecosystems. The 4 other confirmed mass extinctions each deserve their own chapter, but the pattern they reveal together is worth stating clearly. Complex life on Earth has been nearly destroyed 5 times. Each time, the survivors became the ancestors of what followed. The ecosystems that replaced the pre-extinction world were different in fundamental ways. After the Ordovician-Silurian extinction 443 million years ago, fish and land plants diversified. After the Devonian extinction 374 million years ago, the survivors included early tetrapods, the 4-limbed ancestors of all land vertebrates. After the Permian-Triassic event, dinosaurs rose to fill the emptied ecological space. After the Cretaceous-Paleogene extinction 66 million years ago, mammals inherited the planet. Each catastrophe was a door. Something came through it. But the Cretaceous-Paleogene extinction is the one with the most direct evidence of what caused it, because the cause left a mark so distinctive, so global, and so chemically specific that you can find it on every continent on Earth. In mountain ranges, in deserts, on the floors of ancient oceans now exposed as limestone cliffs. It is one of the thinnest layers in the geological record, and it is one of the most important. 66.05 million years ago, an asteroid approximately 12 miles across, about the same width as New York City from the Bronx to Staten Island, entered Earth's atmosphere and struck what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to roughly 100 billion megatons of high explosive. To put that in context, the most powerful nuclear weapon ever detonated by humans released about 50 megatons. The Chicxulub impact was 2 billion times more energetic. In the first seconds, the asteroid vaporized. The rock beneath the impact point vaporized too. A column of superheated material was ejected into space and then rained back down on Earth as molten droplets that solidified into tiny glass beads, called microcrystites, as they fell through the upper atmosphere. These glass beads have been found in sedimentary layers at 52 separate sites worldwide, from Kansas to Italy to New Zealand. The crater left behind, named Chicxulub after a nearby town, measures approximately 124 miles across. Most of it sits under the Gulf of Mexico, but its circular outline is detectable from satellite gravity measurements. The crater's peak ring, a ring of uplifted rock inside the main rim, was drilled by a scientific team in 2016. The cores they pulled up showed rock that had been shocked, melted, and instantly resolidified. The chemical fingerprint of the impactor, including elevated iridium and other elements rare in Earth's crust but common in asteroids, is present throughout. The immediate effects were catastrophic in multiple simultaneous ways. The impact sent a mega tsunami around the Atlantic basin. The heat pulse from re-entering debris ignited wildfires across vast regions of North America. Sulfur dioxide released from vaporized rock in the Yucatan, which is rich in evaporate minerals, combined with water vapor to produce sulfuric acid aerosols that reflected sunlight and cooled the planet for years. A global winter followed. Photosynthesis collapsed. Food chains collapsed with it. Non-avian dinosaurs, which had dominated terrestrial ecosystems for approximately 165 million years, were gone within tens of thousands of years. 3/4 of all species on Earth went extinct, The evidence for this is so thoroughly documented, confirmed across so many independent lines of inquiry, that it stands as one of the best understood catastrophic events in Earth's history. Geophysical data, geochemical data, paleontological data, biological data from the pattern of what survived and what didn't. All of it points to the same moment, but the most striking piece of evidence, the one that crossed the planet with the quiet persistence of a chemical fingerprint, is so thin you could miss it completely if you weren't looking for it. In the hills near Gubbio, Italy, there is a road cut through ancient limestone. Geologists have been visiting this spot for decades. In the layers of rock exposed by the cut, there is a line. A thin, dark clay layer sandwiched between pale limestone below and pale limestone above. The limestone below contains fossil remains of Cretaceous marine life. The limestone above contains none of those species. The clay layer itself is only about a centimeter thick. Hold your index finger and thumb about half an inch apart. That gap is roughly the thickness of the boundary between the world that contained dinosaurs and the world that didn't. In 1980, physicist Luis Alvarez and his geologist son Walter measured the iridium content of that clay layer at Gubbio. Iridium is a platinum group metal that is extraordinarily rare at Earth's surface. The planet's crust contains about 1 part per billion. The clay at Gubbio contained iridium at concentrations 30 times higher, then 60 times higher in other samples, in some locations globally, up to 160 times the background level. Iridium concentrations that high in a thin layer at exactly the same geological moment worldwide have one straightforward explanation: an asteroid. Asteroids and other primitive bodies in the solar system contain iridium at much higher concentrations than Earth's crust, because Earth's iridium sank into the iron core during planetary differentiation. When the Chicxulub impactor vaporized, its iridium dispersed into the atmosphere and settled globally over months to years. This layer, called the Cretaceous-Paleogene boundary, has now been identified in over 350 marine and terrestrial sections on every continent. Scientists have found it in ocean floor sediments drilled by research ships. They have found it in limestone cliffs in Denmark, and chalk beds in England, and marine rock in Japan, and road cuts in New Mexico. It circles the planet at the same geological moment everywhere it is found, consistent to within the resolution of dating methods. The Alvarez hypothesis, named after father and son, was initially controversial. Some scientists preferred volcanic explanations for the extinction, but drilling directly into the Chicxulub crater and recovering core samples showing the same iridium anomaly inside the impact structure removed the last serious objections. The impactor caused the layer. The layer killed the dinosaurs, 1 centimeter of dark clay, found on every continent, marking the moment that opened ecological space for the mammals that would eventually become us. The story of pre-human catastrophe is almost always a story of connection. Every disaster produced survivors. Every extinction opened a door. The asteroid that killed the dinosaurs cleared the ground for everything that came after. But 66 million years ago was not the last time Earth's climate changed violently without any human involvement. 10 million years after the Chicxulub impact, the planet experienced a warming event that looks, in the chemical record, almost exactly like what we are doing to the climate right now. And that similarity is going to matter enormously when we reach the most unsettling chapter in this entire story. 55.8 million years ago, Earth was already warmer than it is today. Crocodilians lived in the Arctic. Palm trees grew in what is now Alaska. The poles were ice-free, and then, over a geological eye blink, the planet got dramatically hotter. The Paleocene-Eocene thermal maximum, confirmed across sedimentary rock on every continent and in ocean floor cores from every major basin, saw global average temperatures rise between 9 and 14 degrees Fahrenheit over a period of roughly 20,000 years. In geological terms, 20,000 years is nearly instant. In human terms, it is still 4 times longer than all of a recorded civilization. The evidence is preserved as a chemical anomaly in the carbon isotope record. Carbon comes in two stable forms: a common heavier version and a rarer lighter version. Living things and certain geological sources, like burning organic material, preferentially release the lighter version. When an enormous amount of light carbon enters the ocean and atmosphere simultaneously, it leaves a distinctive drop in the carbon isotope ratio that geologists call a negative carbon isotope excursion. That excursion is recorded everywhere: in marine sediments in Italy, in carbon in ancient soils in Wyoming, in the chemistry of foraminifera, tiny shell-forming ocean organisms pulled from deep sea cores. The excursion is global, simultaneous, and enormous. It represents an injection of carbon into the Earth system on a scale that dwarfs anything recorded outside of major volcanic events. The leading explanation is volcanic activity associated with the opening of the North Atlantic Ocean. As the continents pulled apart, magma intruded into organic-rich sediments, heating them and releasing thermogenic carbon dioxide at enormous rates. This is confirmed as the most likely trigger, though the precise volume of carbon and the exact rate of release remain actively debated by scientists. The warming that followed had dramatic effects. Deep ocean temperatures rose sharply. Carbonate-secreting organisms in the deep ocean dissolved as the water acidified. Species shifted toward the poles. New mammal groups diversified rapidly, including the earliest ancestors of horses, which appear in the fossil record suddenly during this warming event. Smaller and adapted to a hotter world. The event lasted approximately 200,000 years before the carbon cycle slowly rebalanced and temperatures dropped back toward their baseline. Now, here is why this chapter changes everything that follows. The Paleocene-Eocene thermal maximum looks, in the rock record, nearly identical to what our industrial civilization is currently stamping into the planet's chemistry. A rapid carbon isotope excursion, a sudden temperature spike, ocean acidification, rapid species turnover. The chemical signatures are similar enough that scientists have used this ancient event as the best available natural reference point for understanding our own era's geological footprint. And two scientists, looking at that similarity from a very specific angle, asked a question in 2018 that opened one of the strangest intellectual doors in recent scientific history. If a civilization had existed millions of years ago and burned through its own fossil fuel equivalent and then disappeared, would its geological signal be distinguishable from the Paleocene-Eocene thermal maximum? The answer they reached was deeply uncomfortable. In April 2018, a physicist named Adam Frank from the University of Rochester and a climate scientist named Gavin Schmidt from NASA published a paper in the International Journal of Astrobiology. The paper had a straightforward title and an extraordinary question buried inside it. The question was this: if an industrial civilization had existed on Earth before us, would we be able to find evidence of it in the geological record? They named it the Silurian hypothesis, borrowing the name from a fictional reptilian species in a British science fiction show that predated humanity. Frank and Schmidt were clear from the first paragraph. They did not believe such a civilization existed. They were explicit about that. They said so in the paper. The hypothesis was a thought experiment, a way of probing the detection limits of geology itself. But the question had teeth. And once it was formally asked, it couldn't be unasked. The framing came directly from the Paleocene-Eocene thermal maximum. Frank and Schmidt looked at the carbon isotope excursion from 56 million years ago and asked, if a civilization had caused that signal instead of volcanic activity, what would be different in the rock record? Their answer was troubling. Possibly very little. The chemical signatures of a civilization burning through fossil fuels look remarkably similar to the signatures of large-scale thermogenic carbon release from volcanic intrusions into organic sediments. Both produce rapid carbon isotope excursions. Both spike global temperatures. Both acidify the oceans. Both cause species turnover. The key difference is rate. A civilization might accomplish in centuries what volcanic processes take tens of thousands of years to do. But the faster the rate, the thinner the geological layer, and the thinner the layer, the harder it is to detect and date precisely. Frank and Schmidt calculated what they called the preservation problem. The geological record becomes dramatically thinner and patchier as you go further back in time. Plate tectonics subducts ocean floor every few 100 million years. Erosion grinds continental surfaces down. Very little of the rock record from more than a few tens of millions of years ago survives in exposed, accessible form. The older the event, the more its fine-scale time resolution is smeared by subsequent geological processing. A civilization that rose and fell 50 million years ago, they concluded, would be extremely difficult to detect. A civilization that rose and fell 100 million years ago might be essentially undetectable through any currently available method. A civilization that rose and fell 250 million years ago, during the Triassic, might leave only a faint chemical whisper in rock that has since been recycled, buried, or destroyed. This is confirmed scientific reasoning, applied to a hypothetical scenario. Frank and Schmidt were doing what good scientists do: stress testing assumptions. The assumption they were testing was the assumption that if something significant had happened on this planet, we would know about it. The paper showed that assumption had limits, real, quantifiable limits, and the implications didn't stop at Earth's history. They extended outward to every planet scientists are searching for signs of life. If we can't detect a past industrial civilization on our own planet, what does that say about our ability to detect one on a planet orbiting another star? But before that question opens fully, the detection problem needs to be laid out completely. Because what a civilization actually leaves behind in chemistry and rock is stranger and more specific than most people expect. Frank and Schmidt's paper didn't just ask whether we could detect a past civilization. It asked what kind of civilization we might be able to detect. And that second question produced the most unsettling result of all. A civilization powered by fossil fuels, like ours, stamps the geological record in several ways. Carbon isotope ratios shift rapidly as light biological carbon from burned coal and oil floods the atmosphere. Heavy metals like lead, cadmium, and mercury accumulate in sediments from industrial processes. Nitrogen spikes in soil and ocean sediment from artificial fertilizers. Certain synthetic compounds, plastics and industrial chemicals, appear in layers that didn't contain them before. Temperature proxies in ocean sediment and ice cores record the warming. The package of signals, taken together, is distinctive. Our civilization will be readable in the rock record for tens of millions of years, assuming the rock is preserved. Future geologists, or whatever intelligence examines those rocks, will find a thin layer containing all of these anomalies at the same moment, and will be able to reconstruct that something burned carbon rapidly, altered the nitrogen cycle, spread heavy metals globally, and warmed the planet. The layer will be thin, maybe a centimeter or two, compressed by the weight of rock above it, but the chemical signatures will be there. Now consider a civilization that never burned fossil fuels, a civilization that developed renewable energy, solar, wind, tidal, geothermal, would not produce a carbon isotope excursion. It would not spike heavy metals across global sediments. It would not dump industrial nitrogen into the ocean at scale. It would build cities, but cities are made of materials that weather and dissolve over millions of years. It would use technology, but the metals in that technology would corrode and disperse. Over tens of millions of years, the physical structures of a renewable energy civilization would essentially vanish. What would remain? Possibly some anomalous isotope ratios in specific locations where mining occurred. Possibly trace concentrations of unusual compounds in sediment cores from near urban areas. Possibly a slight perturbation in global temperature records. All of it would be subtle enough to be dismissed as natural variation. Frank and Schmidt called this the sustainability paradox. The more sustainable a civilization is, the less geological evidence it leaves. A civilization that solved its energy and environmental problems cleanly is harder to detect in the rock record than one that burned its way through its planet's resources. This is confirmed reasoning, applied to a theoretical scenario. Frank and Schmidt were not claiming a clean energy predecessor civilization existed. They were demonstrating that the absence of evidence in the geological record cannot be interpreted as evidence of absence, particularly for a civilization that behaved responsibly toward its planet. That logic cuts in multiple directions at once. It means the geological record cannot rule out a predecessor. It also means the geological record might already contain signals we haven't correctly identified yet. And it means any civilization hoping to leave a legible mark on the future needs to behave in ways that are, ironically, environmentally destructive enough to be preserved. The next chapter looks at exactly what chemical signals scientists would search for if they were seriously trying to find a predecessor, because the search methodology is already being discussed in research literature, and it reveals how narrow the window of detection actually is. Physical artifacts don't survive tens of millions of years. A building made of concrete begins dissolving from the moment it's exposed to water and acid rain. Steel corrodes. Plastic fragments and photodegrades over centuries, then millennia. Glass dissolves, slowly in water. Even the most durable human-made materials, fired ceramics, certain synthetic compounds, would be unrecognizable after 100 million years of geological processing. What survives is chemistry. Frank and Schmidt laid out a specific list of chemical signals that an industrial civilization would stamp into sedimentary layers. Each one represents a process that changes the baseline chemistry of rock and ocean sediment in a way that natural geological events don't typically replicate. Carbon isotope excursions are the most prominent. Burning fossil fuels releases carbon from biological sources that have been stored underground for millions of years. This biological carbon carries the light isotope signature of ancient life. Releasing it rapidly into the atmosphere shifts the global carbon isotope ratio in a way that shows up in ocean sediment, cave formations, coral records, and plant material that fossilizes during the event. Heavy metal enrichment is the second signal. Industrial processes concentrate metals like lead, mercury, cadmium, and arsenic in ways that natural weathering doesn't replicate globally. These metals accumulate in lake sediments and ocean floor cores. Scientists already use lead concentration profiles in ice cores to track the rise and fall of Roman metal, smelting, medieval silver mining, and 20th century leaded gasoline. The same technique, scaled up, could theoretically identify industrial activity in far older sediments. Nitrogen isotope anomalies are the third signal. Industrial fertilizer production using the Haber-Bosch process, the method our civilization uses to synthesize ammonia for agriculture, leaves a distinctive nitrogen isotope signature in soil and ocean sediment. A civilization feeding billions of people with artificial fertilizers would spread this signature globally. Polycyclic aromatic hydrocarbons, chemical compounds produced by combustion, are the fourth signal. These compounds are already used by scientists to track wildfire history and early industrial activity in sediment cores. In high concentrations across a global layer, they would indicate widespread burning at a scale beyond natural wildfire. Each of these signals individually has natural explanations. Volcanic eruptions produce carbon anomalies. Natural ore deposits concentrate heavy metals locally. Lightning-caused wildfires produce polycyclic aromatic hydrocarbons. The power of the civilizational signature lies in the combination. All of these signals appearing simultaneously, globally, in a thin layer with a rate of change faster than volcanic processes typically produce. No geological layer older than the human era has been identified that requires a civilizational explanation. Frank and Schmidt confirmed this, but they also confirmed that the search has not been systematic. Nobody has gone through the geological record specifically looking for this combination of signals with the predecessor civilization in mind. The data exists in sediment cores, rock samples, and chemical analyses collected for other purposes. Reading it through this specific lens has barely begun, and sitting right there in the record, 56 million years ago, is an event that matches several of these criteria closely enough that scientists use it as the primary natural reference point. The search is quiet, the evidence is ambiguous, and somewhere in the same conversation, a team affiliated with Harvard decided to ask a different version of the same question, one that science received with considerably less patience. In 2024, a paper appeared in the Journal of Philosophy and Cosmology. Its authors included researchers with affiliations to Harvard and other institutions. The paper proposed what they called the cryptoterrestrial hypothesis. The cryptoterrestrial hypothesis suggested that some unidentified aerial phenomena might be explainable by the existence of intelligent beings concealed within Earth, underground, in deep ocean environments, or on the far side of the Moon. The authors distinguished several versions of the idea: a remnant non-human intelligence that evolved on Earth before humanity, a hidden branch of early human civilization that developed separately and concealed itself, or beings of non-terrestrial origin that established a long-term presence here. The authors themselves described the paper as a speculative thought piece. They acknowledged directly that no physical evidence supported any version of the hypothesis. They framed it as a contribution to the philosophical literature on the search for intelligence and the interpretation of anomalous phenomena. The scientific community's response was fast and largely dismissive. Biologists pointed out that an intelligent species evolving on Earth and remaining concealed for hundreds of thousands of years, through all of human expansion across every ecosystem and geological environment, strains every known principle of ecology and evolutionary biology. Geologists noted that the rock record, which preserves chemical signals from bacteria living 3.5 billion years ago, shows no anomalous signatures requiring intelligent activity before the human era. Physicists noted that underground or deep ocean civilizations would require energy sources, waste products, and physical infrastructure that would leave detectable signals. A Pentagon report released the same year, following years of investigation into unidentified aerial phenomena, found no evidence that any observed phenomenon represented extraterrestrial or non-human technology. The cryptoterrestrial hypothesis is not supported by geological, biological, or physical evidence as currently understood. It is labeled a theory in the loosest sense, really a speculative framework, and sits far outside the scientific consensus. What it shares with the Silurian hypothesis is the underlying question, not the answer. Both ask what we would know if something had come before us. The Silurian hypothesis asks it with geological rigor and arrives at a carefully bounded conclusion about detection limits. The cryptoterrestrial paper asks it with philosophical latitude and arrives at proposals that lack physical grounding. The distinction matters. Frank and Schmidt's work is peer-reviewed science that reveals real limitations in the geological record. The cryptoterrestrial paper is a thought experiment without evidentiary support. But both point toward the same uncomfortable fact. We have only been seriously looking at this planet for a tiny fraction of its history. Our instruments for reading deep time are powerful but imperfect. And the geological record, for all its chemical richness, is fragmentary in ways that can't be fully corrected. The next chapter doesn't speculate. It deals with something confirmed, strange, and deeply unsettling. A moment 42,000 years ago, when Earth's own magnetic field nearly failed, and the consequences that followed. Earth is wrapped in an invisible magnetic field generated by the movement of liquid iron in the planet's outer core. This field extends tens of thousands of miles into space and deflects the constant stream of charged particles flowing from the sun, called the solar wind. Without it, those particles would strip away the upper atmosphere and bombard the surface with radiation that damages DNA, destroys ozone, and makes complex life far more difficult to sustain. 42,000 years ago, the field nearly disappeared. The event is called the Lachance excursion, named after a site in France where the magnetic anomaly was first measured in ancient volcanic rock. During the Lachance excursion, Earth's magnetic poles briefly reversed. The north and south magnetic poles swapped positions, wandered, weakened, and then partially corrected themselves over a period of roughly 800 years. At the event's peak, between 42,400 and 41,500 years ago, the global magnetic field dropped to only 6% of its current strength. 6%. For comparison, a refrigerator magnet holds roughly the same magnetic force relative to a strong electromagnet as 6% holds relative to Earth's normal field. With the magnetic shield that weak, the solar wind had nearly direct access to the upper atmosphere. Cosmic rays, high-energy particles from outside the solar system that the field normally deflects, penetrated far deeper than usual. The ozone layer, which filters ultraviolet radiation from the sun, thinned dramatically as those particles broke apart ozone molecules faster than the atmosphere could replace them. Ultraviolet radiation reaching the surface spiked to levels that would cause severe sunburn in minutes of exposure. Simultaneously, the sun itself entered a period of reduced activity called a grand solar minimum, meaning the heliosphere, the bubble of solar wind that provides a second layer of protection against galactic cosmic rays, also contracted. Both shields failed at the same time. The atmospheric effects were measurable and global. Carbon-14 production in the upper atmosphere surged. Because carbon-14 is created when cosmic rays strike nitrogen molecules. This surge is recorded in ancient kauri trees from New Zealand that were preserved in waterlogged sediments for over 41,000 years, providing a chemical timeline of radiocarbon in the atmosphere with extraordinary precision. Scientists cross-reference that timeline against ice cores from Greenland and Antarctica, cave formations from Europe and Asia, and coral records from the tropics. The signal is consistent across all of them. The same moment, the same chemistry, everywhere at once, and on the ground, something was reacting. When Earth's magnetic field is strong and stable, the northern and southern lights, the auroras, appear only near the poles. Charged particles from the sun spiral down the magnetic field lines and collide with atmospheric gases near the polar regions, producing those green and pink curtains of light in the night sky. The further from the poles you are, the less likely you are to ever see one. During the Lachance excursion, that geography broke down entirely. With the magnetic field at 6% of normal strength, the field lines that normally funnel charged particles toward the poles spread chaotically across much of the planet. Auroras would have appeared at latitudes far closer to the equator than usual. People living across Europe, the Middle East, and parts of Asia and North America would have seen the night sky lit up with moving curtains of light, in colors they had no framework to explain. For early humans already living through a period of climate instability, the sky behavior would have been extraordinary and terrifying. But the light show was the least dangerous part. The ultraviolet radiation increase was the real threat. Ultraviolet radiation at high doses damages DNA, causes rapid sunburning, degrades vision, and suppresses immune function. For mammals spending significant time outdoors during daylight hours, elevated ultraviolet was a genuine survival pressure. The archaeological record at this exact moment shows a dramatic global surge in the use of red ochre. Red ochre is an iron oxide pigment, the same rusty red mineral that colors cave art across Europe, Africa, and Australia. When scientists analyzed red ochre's optical properties, they found it absorbs ultraviolet radiation effectively. Applied to skin, it acts as a natural sunscreen. Humans were already using red ochre before the Lachance excursion, but its use spikes sharply in the archaeological record precisely during the peak of the magnetic field collapse. The timing is too precise to be coincidental. Early humans appear to have responded to increased UV radiation by covering their skin with a mineral that blocked it, possibly without understanding why it helped, but selecting for the behavior because those who used it survived better. The cave art explosion at the same period may carry a related explanation. The famous cave paintings of Europe, Lascaux, Altamira, and dozens of others appear in the archaeological record in large numbers during and just after the Lachamps excursion. Researchers have proposed that early humans retreated into caves during peak ultraviolet hours and began decorating their shelters. The caves themselves provided a radiation shield, ancient humans hiding underground from a failing planetary shield, painting the walls while the sky went strange above them. The next chapter looks at what was happening to the other species sharing the planet during this same event. Because the Lachamps excursion coincides with some extinctions that science hadn't previously connected to a geomagnetic cause, Neanderthals had lived in Europe and Western Asia for roughly 300,000 years when the Lachamps excursion peaked. They had survived previous ice ages, previous warming periods, and previous competition with other hominin species. They were physically robust, cognitively capable, and genetically complex enough to interbreed with early modern humans, which we know because roughly 1 to 4% of the DNA of people with non-African ancestry today is Neanderthal in origin. And then, within a few thousand years of the Lachamps excursion, they were gone from the fossil record. The disappearance of Neanderthals has been debated for decades. Proposed causes include competition with modern humans, interbreeding and absorption into the modern human gene pool, climate change, disease, and various combinations of these factors. The magnetic field collapse had not previously been a major part of the conversation because scientists hadn't connected the Lachamps excursion's precise timing to the extinction event with high enough chronological resolution. The kauri tree data changed that. The ancient kauri trees from New Zealand's waterlogged sediments provided a radiocarbon calibration curve precise enough to allow scientists to redate archaeological and fossil sites across Europe with much higher accuracy than before. When they did, the final confirmed Neanderthal sites in Western Europe aligned closely with the peak of the Lachamps excursion. This doesn't establish a clean single cause. The researchers who published this work were careful to frame the magnetic collapse as a contributing pressure, not a sole explanation. Modern humans were expanding into Europe at the same time. Competition for resources was real, but the elevated ultraviolet radiation, the atmospheric disruption, and the climate instability triggered by the changing solar forcing during the excursion would all have added stress to a population that was already under pressure from multiple directions. A species hit simultaneously by a weakened ozone layer, a changing climate, food competition, and potential disease exposure from contact with modern humans may have crossed a threshold it couldn't recover from. The same event correlated with the collapse of large animal populations in Australia. Giant kangaroos, giant wombats, and other Pleistocene megafauna disappeared from the Australian record during this period. The traditional explanation for Australian megafauna extinction has been human hunting pressure from the first Australians, who arrived roughly 65,000 years ago. The Lachamps excursion adds atmospheric disruption as a concurrent stress on those already pressured populations. Multiple extinctions, multiple continents, the same geomagnetic event as a potential common thread. Earth's magnetic field has reversed more than 500 times in the past 170 million years, which means pre-human life went through this particular catastrophe repeatedly. The Lachamps excursion was not the last close call, and the field is weakening measurably today, though scientists are careful to note that this weakening doesn't necessarily predict an imminent reversal. The scale of these events, magnetic collapses, asteroid impacts, mass extinctions, billion-year-old nuclear reactors, is almost impossible to hold in the mind at once. So the next chapter offers a way to feel the full size of Earth's pre-human history. Kauri trees are massive. A mature kauri can stand 200 feet tall with a trunk 15 feet across. In New Zealand, they grow in the north of the North Island, where the climate is warm and wet. They can live for thousands of years. And when they die and fall into swampy, waterlogged ground, The absence of oxygen in the mud prevents them from rotting in the usual way. Instead, they preserve. Ancient kauri logs have been found buried in northern New Zealand's peat bogs at depth that place them in the Pleistocene. These logs are tens of thousands of years old and still contain intact wood structure, preserved cells, and most crucially, preserved rings. Each ring represents 1 year of growth. Each ring's chemistry reflects the atmosphere of that specific year. The particular chemical record that matters for the Lachamps excursion is radiocarbon, also called carbon-14. Carbon-14 is produced in the upper atmosphere when cosmic rays strike nitrogen atoms. It then gets absorbed by plants through photosynthesis and incorporated into their tissue. When cosmic ray intensity increases, more carbon-14 is produced. When it decreases, less is produced. A tree ring from a year of high cosmic ray bombardment contains more carbon-14 than a ring from a quiet year. By measuring carbon-14 levels year by year through preserved kauri rings spanning the Lachamps excursion period, scientists built a high-resolution chemical timeline of cosmic ray intensity during the event. They could see the surge in carbon-14 as the magnetic field weakened, track its peak during the reversal, and watch it gradually decline as the field recovered. This timeline then became a calibration tool. Radiocarbon dating of other materials, archaeological sites, fossil bones, cave formations, relies on knowing how much carbon-14 was in the atmosphere when the material was formed. If the atmospheric carbon-14 level was unusually high at the time, standard radiocarbon dating will give an age that is too old because the starting concentration was higher than the modern baseline assumed by the calibration. The Corey record allowed scientists to correct for this distortion during the Lachamps period. And when they applied those corrections to archaeological and fossil sites across the world, the timing of events during this period shifted, in some cases by hundreds or thousands of years. Sites that looked too old or too young in uncorrected dates snapped into better alignment with each other. A tree that fell into a swamp 42,000 years ago, preserved by the absence of oxygen in waterlogged sediment, became a precision instrument for recalibrating the history of human and animal populations across the entire planet. The kauri logs are not unique in this. Preserved organic material from other species and other environments contributes to the same reconstructive effort. Scientists build chronologies of deep time by combining every preserved chemical record they can find, each one a narrow window that overlaps with the others, until a coherent picture emerges from the fragments. That picture shows us how violent and transformative Earth's pre-human history was. But it also shows us how much of that history we can still read, even from 42,000 years away. Even from a piece of wood buried in a swamp on the opposite side of the planet from where most of the events occurred. The molecular record goes back further, but it has hard limits. And those limits tell their own story. Ancient DNA is fragile. The molecule that carries genetic information begins degrading the moment an organism dies. Heat accelerates the process. Bacteria consume it. Water destroys it. Even under ideal cold, dry, oxygen-free conditions, the bonds that hold DNA together break down over time, leaving shorter and shorter fragments until nothing readable remains. For most of human history, scientists assumed ancient DNA could survive for only tens of thousands of years at most. Then, preservation conditions in permafrost and cold caves pushed that limit back. Woolly mammoths, frozen in Siberian permafrost, yielded readable DNA. Neanderthal bones from cold European caves produced enough genetic material to sequence the Neanderthal genome. The limit kept moving. In 2023, scientists announced a new record. DNA recovered from sediment cores drilled in northern Greenland, from layers deposited approximately 2 million years ago. The DNA came from a remarkable collection of organisms. Plant species related to mastodons and geese and reindeer and horseshoe crabs, and dozens of other organisms were identified from the fragments. painting a picture of a warm, forested Greenland ecosystem that existed 2 million years before the present, when the region's climate was dramatically different from the ice-covered landscape it carries today. 2 million years is the current outer limit of DNA recovery. Beyond that, the molecule is too fragmented to yield reliable sequence information, regardless of how good the preservation conditions are. Proteins last longer. The three-dimensional shape of protein molecules, held together by different chemical bonds than DNA, resist degradation better over geological time. In 2022, scientists reported recovering ancient proteins from a rhinoceros tooth fossil from the Miocene epoch, dated at between 21 and 24 million years old. The amino acid sequences recovered were partial, degraded, and required sophisticated analysis to interpret. But they were real. They confirmed biological relationships that couldn't be tested through DNA because the DNA was long gone. Beyond proteins, molecular biology falls essentially silent. The specific biological molecules that carry the most detailed information, DNA, RNA, proteins with readable sequences, degrade past the point of recovery. What survives beyond 24 million years is chemistry, not biology. Isotope ratios, elemental concentrations, molecular fragments too degraded to carry biological information, but still detectable as organic in origin. This creates a hard boundary in what we can learn about pre-human life. For the last 2 million years, we can read genomes. For the last 24 million years, we can read proteins. Beyond that, we read rocks. And rocks, as every chapter in this story has shown, are extraordinarily readable once you know the language. Carbon isotopes, sulfur fractionation, mineral chemistry, sedimentary structures. These signals span billions of years and carry the history of everything that lived and died, and transformed this planet before any human drew breath. That gap between what molecules can tell us and what rocks can tell us is where the most interesting questions live. Because it's also the gap in which, if the Silurian hypothesis were ever confirmed, the evidence would have to be found. The next chapter brings the entire history together in one image, a single day on a clock. 24 hours representing 4.5 billion years. And the position of everything in this story, from the Jack Hill zircon to the Lachance excursion, mapped onto that clock face. 4.5 billion years compressed into 24 hours. Every chapter of this story placed on a clock face, midnight, Earth forms from the solar nebula. The planet is liquid rock, glowing orange, bombarded by debris from a still-forming solar system. 12 minutes past midnight. The Jack Hill's zircon crystallizes. The oldest known piece of Earth. Liquid water is already present on the surface. 23 minutes past midnight. The potentially biogenic carbon in the 4.1 billion year old Jack Hill's zircon. A chemical whisper of life, too faint to confirm, too specific to ignore. Around 30 minutes past midnight. The oldest microfossils in the Nuvuagituk belt, minimum confirmed age. Life in the dark, around hydrothermal vents, eating minerals instead of sunlight. 45 minutes past midnight. The Dresser Formation stromatolites, the oldest unambiguous complex microbial life. Cyanobacteria are already building. 2:30 in the morning. The great oxygenation event begins. Cyanobacteria have saturated the ocean's iron-absorbing capacity. Oxygen crosses the atmospheric threshold. The largest mass extinction in the history of life begins quietly, invisibly, in chemistry. 4:30 in the morning. The natural nuclear fission reactors at Oklo, Gabon, ignite. They will run for several 100,000 years, cycling on and off, processing fuel, containing their own waste, before exhausting themselves. 8:30 in the morning. Possible earliest animals, sponge-like fossils in South Australia. Complex multicellular life begins its first experiments. 9:15 in the morning. The Ediacaran period. Dickinsonia, Hautia, Rangermorphs. Soft, mouthless, possibly immobile animals covering the seafloor informs evolution will never try again. 10 in the morning. The Cambrian explosion. Hard shells appear. Eyes appear. Predators appear. The fossil record fills up with complexity that had already been building for tens of millions of years. Between 10 in the morning and 9 at night. 5 mass extinctions. The Ordovician Silurian, the Devonian, the Permian Triassic, the Triassic Jurassic, each one nearly ending the story, each one replaced by a rebuilt biosphere. 9 in the evening. The Chicxulub asteroid strikes the Yucatan. The non-avian dinosaurs, which have dominated for the equivalent of the entire afternoon, are gone by 9:15. Mammals step into the open space they leave behind. 9:40 in the evening. The Paleocene-Eocene thermal maximum. The planet spikes 9 to 14 degrees Fahrenheit in 20,000 years. Early horses appear, smaller and faster, adapted to a hotter world. The warming eventually fades. 11:59 in the evening, 45 seconds before midnight. The Lachamps excursion. Earth's magnetic shield drops to 6%. Early humans paint cave walls. Neanderthals disappear. 11:59 and 54 seconds. Homo sapiens first appears. 6 seconds before midnight. Every human civilization, every invention, every city, every war, every scientific discovery, every piece of music ever written, every language ever spoken, the entire span of recorded human history. 6 seconds. Everything in this video, every ancient microbe, every mass extinction, every asteroid, every magnetic collapse, every speculative hypothesis about what came before us, happened in the 23 hours, 59 minutes, and 54 seconds before those 6 seconds began. The planet did not wait for us, and it will not stop when we are gone. Scientists already have a name for the geological epoch defined by human activity, the Anthropocene. The word means the age of humans. Its formal definition is still debated by the scientific community, with different researchers proposing different starting dates ranging from the beginning of agriculture to the first nuclear weapons tests in 1945, which left a layer of radioactive isotopes in sediments worldwide that is globally synchronous and chemically unmistakable. Regardless of the precise starting line, what is confirmed is this. Future geologists will be able to identify a thin layer in the rock record that marks the human era as clearly as the iridium layer marks the Chicxulub impact. That layer will contain a specific package of signals, a sharp negative carbon isotope excursion from burning fossil fuels, a spike in heavy metals from industrial processes, a global enrichment of nitrogen from artificial fertilizer production, the presence of microplastics in marine sediment, specific synthetic organic compounds that don't occur naturally, radioactive isotopes from nuclear testing spread in measurable concentrations across the globe, a surge in fly ash, the microscopic spherical particles produced by coal combustion found in lake sediments on every continent. Each of these signals is already measurable in sediment cores being pulled today. Scientists studying lake beds in rural Canada find microplastics and coal fly ash in layers from the mid-20th century, thousands of miles from the nearest factory. The chemical reach of industrial civilization is genuinely planetary. The layer will be thin, compressed by the weight of rock deposited above it over millions of years. The entire human industrial era might eventually be a few centimeters of chemically enriched sediment, thin enough to hold between 2 fingers, just like the iridium layer from the asteroid that killed the dinosaurs. Future intelligence examining that layer, whether human descendants, evolved successors, or something we cannot currently imagine, will know that something happened here. Something changed the chemistry of the atmosphere rapidly. Something spread metals across the global ocean. Something produced compounds that geology doesn't make on its own. They will be able to read those signals the same way we read the iridium layer, the same way we read the carbon isotope excursion of the Paleocene-Eocene thermal maximum, The same way we read the sulfur fractionation signature of the Great Oxygenation Event. Chemistry is the most durable language on this planet. It survives when everything else fails. It outlasts bones, outlasts buildings, outlasts civilizations, outlasts species. The rock record does not care what caused a signal. It simply preserves it. Which means everything we have done and everything we do from this moment forward is being written into stone, permanently, legibly, in a language that will still be readable 50 million years from now. There is a thread running through every chapter of this story, and it is worth pulling tight at the end. Cyanobacteria did not choose to transform the atmosphere. They had no awareness of what they were doing. They photosynthesized. They released oxygen as waste, as, for hundreds of millions of years, the chemistry of the planet absorbed that waste. When it couldn't anymore, the atmosphere changed. Every complex organism that ever lived, including every human being, owes its biological existence to microbes that had no idea they were building the future. The Chicxulub asteroid didn't choose to open ecological space for mammals. It was a rock following orbital mechanics. It hit. It vaporized. It spread iridium around the planet. 76% of species went extinct. Mammals diversified into the emptied niches. The asteroid had no purpose, no awareness, no intention. It just happened, and the consequences of it happening include the existence of primates, and eventually, you. Cyanobacteria didn't know. The asteroid didn't know. The Oklo uranium deposit didn't know it was running a nuclear reactor. The Ediacaran organisms didn't know they were laying the architectural groundwork for the Cambrian explosion. The Lacham's geomagnetic excursion didn't know it was pressuring Neanderthals toward extinction while driving early humans into caves to paint their walls. None of it was intentional. All of it was consequential. We are the first thing on this planet that knows what it is doing to the planet. We read the geological record. We measure the carbon isotope excursion we are creating in real time. We know about the iridium layer and what caused it. We know about the Great Oxygenation Event and its aftermath. We know that our industrial activity is stamping a permanent chemical signature into the rock record that will be readable for tens of millions of years. Cyanobacteria accidentally poisoned the world with oxygen and accidentally made all complex life possible. We know we are doing something. We can see the signals accumulating. The question that Frank and Schmidt embedded in the Silurian hypothesis, would we recognize a predecessor civilization in the geological record, pulls, on reflection, in both directions. Can the future recognize us in the geological record? Yes, definitively. The layer is already forming, the chemicals are already spreading, the signal is already being written. Can we recognize ourselves in what we're doing, in real time, the way the geological record will show it to future eyes? That question doesn't have a geological answer. It has a human one. Adam Frank and Gavin Schmidt published the Silurian hypothesis as a paper about detection limits in geology, and it is that. Every methodological conclusion they reached is valid and confirmed within its stated scope. But the paper does something else. It forces a specific kind of humility. For most of human history, we assumed we were the first intelligent, technology-using species on this planet. We assumed this partly because no evidence contradicted it, and partly because the assumption was never formally examined. Nobody wrote a paper asking whether the geological record could contain evidence of a predecessor. Nobody calculated what that evidence would look like or how detectable it would be. The assumption was invisible because it was never questioned. Frank and Schmidt questioned it. Their answer was not that a predecessor existed. Their answer was that we cannot be completely certain it didn't, because our detection methods have limits that are real, quantifiable, and in some cases severe. A civilization that rose and fell tens of millions of years ago, particularly one that used clean energy, might leave a geological signal too faint to distinguish from natural variation. That is a statement about epistemology, about the limits of what we can know, as much as it is a statement about geology. It connects to the broader question of life in the cosmos. The Fermi paradox asks, why, Given the age and size of the universe, we haven't detected signs of other intelligent civilizations. One answer Frank has explored in other work is that civilizations may routinely reach a point where they transform their planet's chemistry, consume available resources, and destabilize their own conditions for survival. The geological record of Earth might contain hints about whether that pattern is real or not. If the Paleocene-Eocene thermal maximum was caused by volcanic activity, it tells us something about how planets naturally destabilize their own climate systems. If it were ever demonstrated, hypothetically, to contain a civilizational signal, it would tell us something much darker about the typical fate of intelligent species. Frank and Schmidt were not writing science fiction. They were doing what the best science does, taking a question nobody thought to ask formally and asking it with enough rigor to produce a real answer, even if the answer is primarily about the limits of knowledge rather than about a confirmed discovery. The planet was here for 4.5 billion years before us. It will be here for billions more after us. The question of what came before and what comes after and what leaves a readable mark on the rock is a question with no fully satisfying answer. But it is the right question. Every major extinction in Earth's history produced a different world on the other side. The pattern is consistent enough that some scientists have proposed it as a general principle. Catastrophic disruption of an established ecosystem does not destroy life, it redirects it. The Ordovician Silurian extinction, 443 million years ago, killed roughly 85% of species. Most victims were marine invertebrates adapted to the warm, shallow seas of the Ordovician. What survived diversified into a world with different ocean chemistry, different temperatures, and different competitive pressures. Fish diversified dramatically in the Silurian. Vascular plants established themselves on land. The Devonian extinction, 374 million years ago, killed roughly 75% of species and specifically devastated reef ecosystems. The recovery opened space for early tetrapods, four-limbed vertebrates, to establish themselves on land. Every land vertebrate alive today, every reptile, every amphibian, every mammal, every bird descends from the survivors of the Devonian extinction. The Permian-Triassic extinction, the Great Dying, killed 96% of marine species and 70% of terrestrial vertebrate species. Its aftermath was the slowest recovery in the fossil record, roughly 10 million years. What rebuilt in that time was a fundamentally different biological world. Archosaurs, the group that includes dinosaurs, crocodilians, and eventually birds, dominated the Triassic recovery. Mammals were present but small. The Triassic-Jurassic extinction, 201 million years ago, cleared the ecological space that allowed dinosaurs to dominate. Before this event, dinosaurs were one of several competing archosaur groups. After it, they ran the terrestrial world for 135 million years. The Cretaceous-Paleogene extinction cleared that world and gave it to the mammals. Within 10 million years of the Chicxulub impact, the diversity of mammalian body plans, sizes, and ecological roles exploded. Whales were on their way to the ocean. Bats were on their way to the sky. Primates were in the trees. 5 doors, 5 transformations, each one erasing a dominant order and replacing it with something that could not have existed before, because the previous occupants were in the way. The living world is not a stable system that disruption damages. It is a dynamic system that disruption transforms. The pre-human history of this planet is a history of transformation after transformation, each one building on the wreckage of the last. We are the current occupants of a world built by catastrophe. And the rock record suggests, with geological certainty, that the transformations are not finished. The oldest legible record on this planet is not written in words or symbols. It is written in atoms. A zircon crystal from Western Australia holds the atomic record of liquid water from 4.4 billion years ago. Banded iron formations in rock layers across 3 continents hold the record of cyanobacteria dumping oxygen into ancient seas. The Oklo-uranium deposit in Gabon holds the isotopic record of a nuclear chain reaction that nobody witnessed. The KPG boundary clay holds the record of an asteroid impact that ended the Mesozoic era. Ice cores from Antarctica hold the record of every major atmospheric event of the past 800,000 years in their chemical layers. Each of these records is written in the same language: isotope ratios, elemental concentrations, mineral structures, crystal chemistry. The language is universal and ancient and indifferent to what caused the signal. A volcanic eruption writes in this language. A meteorite writes in this language. A living bacterium writes in this language. A burning coal seam writes in this language. The records overlap and confirm each other. The carbon isotope excursion of the Paleocene-Eocene thermal maximum appears in marine sediments from Italy, in soil carbonates from Wyoming, in the chemistry of ancient ocean organisms from cores drilled in every major ocean basin. The iridium anomaly of the KPG boundary appears in limestone in Italy, in chalk in England, in ocean floor sediment from the Pacific, in road cuts in New Mexico. The magnetic reversal of the Lachance excursion appears in volcanic rock in France, in kauri tree rings in New Zealand, in cave formations in China, in ice cores from Greenland. Global events write global records. The planet is its own archive. We have been reading that archive for less than 2 centuries with any systematic rigor. Radiocarbon dating was invented in 1949. Mass spectrometry, capable of measuring isotope ratios precisely enough to read geological chemistry, came later still. The technology for drilling deep ocean sediment cores and recovering them without contamination developed through the second half of the 20th century. In less than a human lifetime of serious reading, we have decoded 4.5 billion years of planetary history, imperfectly, with gaps, with debates that remain unresolved. But the outline is clear, and it is extraordinary. Life appeared almost immediately on a cooling planet. It transformed the atmosphere. It built visible structures that still exist. It survived 5 near-total destructions. It was interrupted by cosmic violence. It rebuilt each time, stranger and more complex than before. And somewhere in that history, the question Frank and Schmidt asked remains open. Whether something came before us that was aware or organized or technological, we do not know with certainty. The geological record sets limits on what it can confirm. What it can confirm is everything else in this story. And everything else in this story is enough to permanently change the way you think about the ground beneath your feet. 50 million years from now, the continents will have moved. North America will be pushing against Asia. The Mediterranean Sea will be closed. The Himalayan mountains will have eroded to hills. The geography of the planet will be largely unrecognizable. But somewhere in the sedimentary rock of that future world, compressed under hundreds of feet of accumulated stone, there will be a layer, a thin stripe of chemically enriched sediment, a few centimeters thick, containing elevated heavy metals, a carbon isotope excursion, microplastic fragments, radioactive isotopes from nuclear tests, the molecular signatures of combustion on an industrial scale. That layer will be readable. The chemistry doesn't degrade on geological timescales. The isotope ratios will still carry their information. Whatever intelligence examines those rocks, with whatever instruments it has developed, will be able to see that something happened at that moment in Earth's chemical history. Something rapid. Something global. Something that burned carbon and spread metals and changed the atmosphere in ways that natural processes don't replicate at that speed. They will be asking the same question Frank and Schmidt asked in 2018, but pointed backward at us instead of at a hypothetical predecessor. They will ask, was this caused by something intelligent? Was this the signature of a civilization? Can we detect evidence of organized, intentional activity in this chemical stripe? And they will face the same detection problems Frank and Schmidt described. A thin layer, smeared time resolution, ambiguous signals that could have natural explanations, physical artifacts long since dissolved, corroded, eroded, or subducted. What they find in that layer is being determined right now. The thickness of the layer, the intensity of the signals, the diversity of the chemical markers, all of it is being written by decisions being made by 8 billion people living on the surface of this planet today. That is the sharpest edge of everything in this story. The Jack Hill zircon recorded liquid water passively. The cyanobacteria transformed the atmosphere accidentally. The asteroid stamped the iridium layer without choosing to. Every pre-human force that wrote its chemistry into the rock did so without awareness of what it was doing or what it meant. We are the first system on this planet that knows it is writing the record. We can read the language we are writing in. We know what the signal will look like. We know what questions it will raise for whatever comes after us. The entire 4.5 billion year history of this planet, from the Jack Hill zircon to the Ediacaran animals, to the Oklo reactor, to the Chicxulub impact, to the Lachamps excursion, to the Silurian hypothesis, builds to this moment. The moment when the thing doing the writing knows it is writing. The rock will remember. The chemistry will preserve. The archive will be there. The only question left is what it says.